Science on Surfaces.
Welcome to this podcast. Today we will talk about nanoplasmonic sensing, also called NPS. We will talk about what NPS is, what information you can get from this, and how it is measured. Here with me in the studio I have Dr. Elin Langhammer. She's founder and technical director of Insplorion, a company that develops and manufactures NPS sensors for research and development instruments, and also large volume sensor applications. Elin has a PhD in material science, and she's one of the inventors of Insplorion's NPS technology. She's currently responsible for sensor development and IPR at Insplorion. So welcome.
Thank you very much.
It's great to have you here. So let's just dive into it and start with the basics. So what is nanoplasmonic sensing?
It's optical technology. It's a platform technology that makes it possible to measure small changes on the nanoscale, in materials on the nanoscale. So you can measure, for example, changes in thin films or in nanoparticles or molecular absorption to the sensor surface.
So this is always near a surface or related to surfaces somehow?
In our case, it's always on a surface because we immobilize our nanoparticles, that is the actual sensing element, on a surface. It's in principle also possible to use them in a solution phase, but we immobilize them on the surface because it's much more versatile and more easy to handle them that way.
Okay, so how, if you can just describe how the sensor is designed and how it works?
So we have usually it's a planar glass substrate onto which we immobilize nanoparticles. So in our case, it's usually gold nanoparticles that have a diameter about 100 nanometers and 20 nanometers high, so gold discs. And the sensor works in a way that we shine light onto these nanoparticles, and they then act as small antenna and probe their close environment. And then they send back to us a signal, a light signal that has been slightly altered, changed. And the change in this light signal depends on the refractive index of the medium close to the nanoparticles. So the nanoparticles probe their close environment, and then they send back a slightly altered light signal that gives us information about their surrounding.
Mm-hmm. So what could it be in their surrounding that they are sensing?
So in simple terms, it's they detect changes in refractive index or dielectric function of materials. So if we're considering, for example, a biomolecular absorption event, then we replace the buffer or the solution that has been close to the sensor surface at the beginning with biomolecules. And biomolecules have a higher refractive index than the solution, and therefore we see a change in our optical signal.
Okay.
But it could also be, for example, we could monitor the glass transition, the polymer phase transition.
And what is that?
It's a change in the polymer properties that occur at a certain temperature. Mm-hmm. And we can also see that kind of change then because it's before or at a lower temperature than the glass transition, and at a higher temperature the polymer will respond differently to changes in the temperature.
So it's not the temperature itself, but it's more the molecular arrangement.
Yeah, exactly. The arrangement of the molecules inside the polymer makes it respond differently to a temperature rise, and therefore we can see that at this temperature it changed, the behavior of the polymer changed, and therefore we can detect glass phase transition.
Okay. So you can sense absorption and desorption events, like molecules absorbing to the surface or leaving the surface, and also that they change sort of internally?
Yeah, it can also be like a conformation change, like a protein changing its shape, or if it's standing up or lying down on the surface, it will alter the signal. We also have a customer who's using, or a few customers using our instrument for catalysis applications. So looking at small catalyst particles and seeing when they oxidize and reduce, for example, when you then change the environment and also the temperature, and then you can see when they actually go through the reduction and oxidation processes. So it's a highly versatile technology, and you can do many different things with it.
So you say nanoplasmonic sensing, so if you compare to standard plasmonic sensing, like if you can call it standard, I'm thinking of like the SPR.
Surface plasmonic.
Yeah, exactly.
resonance.
Yeah. So what is the difference if you compare to that?
There is a few differences. The one that you maybe notice the most as a user of the instrument is that in our case we have a higher, or we're more surface sensitive or surface discriminative. So we detect things happening very close to the surface within maybe 50 nanometers from the sensor surface. While in SPR, or surface plasmonic resonance, it's about 10 times as large sensing depth, so you can detect changes occurring much further away from the surface. But very close to the surface, we have a higher sensitivity, and we can detect smaller changes in the materials. It's also less temperature sensitive, our technology, which means that we don't need that sophisticated temperature control. We are not so sensitive to disturbances in the room or in the environment, and that makes it very robust, the technique, and that's why we can use it in these large-scale sensor applications. Okay.
But the principle, like the physical principle, so to say, is the same?
It is the same. It's the difference is that in SPR you need or you use a metal film that has a nanoscale dimension in one direction, but then it's an elongated film. While we use nanoparticles that where all scales are below the wavelength of light. And that makes a difference in the instrument setup. While we can, the LSPR or the NPS can be excited with light coming in from basically any angle, or it's quite robust in that sense. While in the SPR you need usually you use a glass prism to excite the plasma resonance, and which is a little bit more sensitive optical equipment.
Okay. So we talked a bit about what information you can get or what things you can measure. But how would you typically then do a measurement?
It of course depends a lot on what the measurement is, since it can be used for so many different things. The principle of all measurements is that you use typically a white light source and a spectrophotometer, and then we monitor the change in the light signal after it has interacted with the nanoparticles.
So white light is just like a plain lamp?
Yeah, just a plain normal halogen lamp.
Yeah.
But then it depends a lot on what you actually want to measure. If we consider, for example, like a biomolecular absorption to surface, then you would you would clean the sensor and these things, of course, but then you would put it into a fluidic chamber, and typically you would start flowing your buffer solution over the sensor to see that you get a stable baseline and so on, and then you absorb or insert your proteins, and then you will see a shift in the plasmonic resonance or in the optical signal, and this shift is then proportional to the amount of proteins that have bound to the surface. So
you get a time-resolved measurement of the absorption,
and you can monitor your experiment in real time during the measurement.
And How long does it typically take to do such a measurement?
That of course also depends on the measurement you want to do.
Yeah.
The preparation time is short. You only need to clean the sensor, clean the measurement chamber. Maybe you want to functionalize your sensor surface in some way. But then, like returning to the protein absorption experiment that we talked about, it could take maybe an hour to do such an experiment. But it of course depends on the protein in question and the concentration and so on.
And what you want to study, of course.
Yeah, if you want to do temperature sweeps and look at oxidation of nanoparticles, that's a little bit more time required to do that, depending on how fast you want to sweep the temperature and so on. So it's very difficult to really say how long the measurement takes. If we consider our air quality sensor or NO2 sensor that we have recently entered the market with, that sensor will be used continuously through weeks and months and years, and will continuously measure changes in the NO2 concentration. So then it's a very long measurement.
Yes, of course. So let's talk a bit more about that. So this is the same sensor, but in a completely different context, so to say.
The basic technology is the same, so it's the same nanoplasmonic sensor. We have a glass surface with our nanoparticles on it, but then we put on a functional layer on top of the surface. So this functional layer then interacts specifically and selectively with NO2 and give rise to a signal. So it's a change in the optical properties of this functional layer that we detect.
Okay.
So in that way we can design the sensor to work with various gases by changing that functional layer to interact with different gas molecules.
But it will be one functional layer at a time. So you have then one sensor per whatever molecule you would like to detect, or
yes, like most likely it would be one sensor per gas, or it could be that to get more information, like if there is rapid changes maybe in the concentration and things like that, you could also consider having different thicknesses of the functional layer. So it could be advantageous to maybe use also several sensing areas with the same functional layer but slightly modified sensitivity in some way.
But how does it work over time? If you said that you would have this active then, or working for like months or something like that, and I'm thinking they will pick up, or the gases will absorb to this sensing layer. Will it not be like saturated, or?
No, it's balance. So we also have molecules desorbing. So when the concentration in the surrounding is lowered, then more NO2 will be released from the functional layer, and so the signal we see is concentration dependent, and it will work in real time. So it will measure both when its concentration increases, the signal will increase, and then it decreases, and the signal will decrease.
So you can actually then probe the concentration in the surrounding air.
Yes,
for
exactly.
months at a time, or
exactly. Like so by measuring continuously, we see now it increased and then it decreased, and this is very important information to have, both if you consider when planning the streets or making tunnels or drawing the traffic in a city, for example. Then you can maybe monitor before you make the change, and then after you made a change to see that it actually had an effect what we did. But it's also of course also usable just to see where where do you actually have air quality problems, where maybe where do you need to do something about it.
Yeah, I'm thinking about city environments in general, right? It would be it's relevant to monitor the air quality in cities.
Yes, especially the larger cities, like in China, where they have a lot of problems with air quality. There it's of interest to monitor both, so you see maybe in which park should you go running, so see where is the best air. It's also of interest to know what daycare centers have the best air, because you want your kids to be healthy and have as good air as possible. You want to have good air in your apartment, at the workplace. So in cities that have worse air than Gothenburg, it's even larger problems than we have.
Okay, so what are the challenges, or doing such a measurement? Is there anything that you need to keep in mind or consider, or that is like a difficult aspect?
I think one of the main things to keep in mind is this, that we touched upon, that we are very have a high surface sensitivity, but the sensitivity decays very rapidly from the surface. So if you have a thick film, you will only probe the innermost portion of that film. And that can sometimes be problematic. It's like if you want to have look at molecular absorption onto protein or polymer film, then it's difficult to make the polymer film thin enough that you can actually monitor that. On the other hand, it can also be advantageous because, like we discussed, measuring the glass transition temperature in polymers, it's sometimes of interest because these glass transition temperatures will be influenced by different interfaces. So the surface will influence it, and the interface towards air or the surrounding environment will also influence it. So maybe you want to monitor this temperature close to the surface, and then we can do that because we are that surface sensitive.
And what did you say the probing range was, or the thickness limit, so to say?
I think I would say that we have a sensitivity to up to maybe 50 nanometers from the sensor surface, but the sensitivity decays rapidly from the surface. It's an exponential decay. So the closer you are to the surface, the larger the signal will be. So if you're 50 nanometers away, it has to be a quite big change for you to actually detect that.
And this challenge is then relevant for when you do like work with biomolecules or films, like thin films, maybe more in a lab environment then. Because I guess if you then talk about the like in the air quality sensor case, you will never reach those thicknesses, or will you?
No, there we can of course design it away so we know it works well with our sensing technology. But yes, if you have biomolecular absorption where you have an antigen and then an antibody and then maybe another antigen or something like this, then you quite rapidly move away from the surface and the sensitivity will decrease.
Any other challenges that you need to, or things that you need to keep in mind when you do a measurement?
It's, I guess, the normal or usual thing, I guess, when you do liquid phase measurements, it's good to maybe degas your liquids to not have problems with air bubbles, although we're not very sensitive to that, and it works actually quite okay anyway, but it can be good to get the best quality from...
What would they do, air bubbles?
The air bubbles can, if they go onto your sensor surface, then they will drastically change the signal and disturb the signal because air has a very low refractive index, and then change the signal drastically. So, and it's difficult to get rid of them once you have them. So it's good to avoid getting them.
Mm-hmm. So what do you think about the future of this technology in these different application areas? Or maybe even other application areas that we haven't talked about?
Yeah, it's I think we will see, or we are working to bring to the market several new products with this sensor technology. We will continue working with our research instrument, improving them and selling them. But the main advancements will be in the large-scale sensor applications. We touched on the air quality sensor several times. It's a highly versatile platform that we have been building. We recently entered the market with the NO2 sensor, and now we are moving on to other gases as well. We had a grant application that was approved together with PowerCell. So we recently started collaborating with PowerCell. So now the next gas will actually be hydrogen.
Okay.
But then in the future, we will also develop a sensor for air quality that has sensitivity to several gases like ozone and carbon monoxide and other gases that are problematic.
It can be basically any gas that you sense, or are there any?
In principle, yes. The trick is to design this functional layer in a way that it actually interacts as selectively and sensitively as possible with that particular gas.
Okay.
And then what we haven't talked about is actually we are also developing a battery sensor, a sensor for lithium-ion batteries that will be used to get more information about the battery status, like the battery battery state of charge, the charge level, and the health of the battery. It can also aid in detecting catastrophic failures at an early time.
Yeah.
So this sensor will have a large impact on the transition to renewable energy, since today the lithium-ion batteries are a limiting factor in the transition, because they are still quite expensive. The energy density is too low, making them heavy, and also the risk, of course, of catastrophic failures is scary, and you maybe don't want to have a lithium-ion battery storage inside your house or in your car, because if something happens, it's dangerous. Yeah.
So what is it that you're sensing then with the batteries?
In that case, we're measuring directly on the battery materials.
So inside?
We put it inside the battery cell, and close to one of the electrodes, so either the cathode or the anode. And when the battery is charged and discharged, the anode and cathode will take up and release lithium ions. So you have a chemical change occurring there. It's also a structural change. So we monitor these changes in the battery materials or the electrode materials.
So the sensor is it on the electrode, or is it just near?
It's pressed against the electrode.
So it's close to the surface that you mentioned.
It's very close to the surface, yes, so that we can actually monitor changes in the electrode materials.
Okay. And then you can say something about the electrode status or the charge level, or?
Yeah, then you can say something about the charge level, because you can see how much lithium is stored inside the electrode material. You can also say something about the health of the battery cell. It's talking about battery health means a lot of different things to different people, but in principle, the health can be measured as a decrease in the battery capacity, meaning that if you have a battery that is aging, you will not be able to store as much energy into it. And then we can measure that that change in the capacity of the battery cell. We can also measure the temperature inside a cell, which then gives indications of when a catastrophic failure might be on its way, because then the temperature increases very rapidly.
Yeah.
And today you only measure the temperature outside the cell, and they can differ quite a lot actually, with like 20 degrees or so, because if it's a quick, rapid change that occurs.
But then this measurement will be like years long, like for the battery lifetime, which could be then years.
That's of course a challenge to make the sensor stable enough, because you don't want to change, or depends on the application, but in a car, for example, you want the battery to last at least 10 years. So then the sensor should also last that long.
And will you capture the information then this whole time? Or will you just measure now and then?
It may not be... I don't think it's necessary to measure every second or every millisecond or something like very high time resolution, but maybe every minute you would do it.
For 10 years.
Then it's important, of course, to find out which part of the information is important. You cannot continue measuring complete optical spectra for that long. There will be a lot of information, but by capturing the important parts of the information. And that we also believe will help then in what's commonly referred to as second life. Like after a battery has been used in an electric vehicle, it can maybe be used in a less demanding application, like an energy storage or something like that.
Okay.
And today that's very difficult, because you don't really know the status of your battery, you don't know the health of the battery, and you don't know, then you don't know how to put a price on it. Then does anyone give a warranty for that kind of battery? Do you dare to buy it, because you don't really know what you're buying, and so on. So, but if you get a second life market to be more active and actually start working in a good way, then you can save both a lot of energy and raw materials, because the batteries can be used for an extended period of time. And it will also, of course, decrease the price of the batteries, because they have a use also after they've been used in a demanding application like a vehicle.
Yeah, sounds very useful. So any other key areas where this could go into or is going into?
We, of course, look at different applications all the time, and where we can find our sensor useful. But today, that's the main areas that we're targeting is the lithium-ion battery sensor, an air quality sensor for more gases than NO2, and a hydrogen sensor, where we are still looking into where the main market could be, where is the need the largest, where can we actually fill the requirements that market needs, and so on. So we have more market intel to do there, but it's of course extremely interesting and fun that we have gotten PowerCell on board, and that we will be able to do tests in their fuel cells.
Yeah, and then of course you mentioned the lab version, which you refer to as the research instrument.
Yes, a research development tool,
which can go into
where today we have 3 different instruments. So we have one for gas phase measurements that can actually measure up to 600 degrees, so very high temperatures to compare to many other techniques. We have a liquid phase instrument, a standalone liquid phase instrument, as mainly used then for bioscience applications. And we also have a combination instruments combined with the QCMD, which we call the Acolyte. We are both looking at improving our instruments, but it's also likely that we maybe develop some additional instrument in the future, for example, fiber optic based instrument for battery research and development, which then goes hand in hand a little bit with our battery sensor development.
So a technology that can be packaged in many different ways, you can say.
Yes, exactly. Very versatile, but which is, of course, extremely challenging in a way, but also makes it very powerful technology. And when we have a platform that works, we can use it in many different ways.
Okay, I think that's what we had for today. So thank you for listening to this episode with me, Malin Edvardsson, and Dr. Elin Langhammer from Insplorion. And I would also like to take the opportunity to mention to those of you who are listening or watching that if you are interested in surface science and related phenomena, you should check out our blog, the Surface Science blog. Thank you.